So, as we had discussed that in Mpls, the packets are classified at the ingress of the Mpls domain into forwarding equivalence class, and then each FEC is bound to a label, and the label bindings between the FEC and the labels and the label bindings between the FEC and the labels are then distributed to the label switch routers through a separate protocol which is called as label distribution protocol. Now, let us see how the label allocation is done in the MPLS networks. Now, as I was saying in the previous lecture, that label allocation can be done either based on downstream based label allocations or upstream based label allocations. Okay. So, let us look at what are the various techniques. Now, in downstream based label allocations, it could be of two types: downstream unsolicited. Okay. Now, downstream unsolicited, the label assignment is done by the downstream peers and then it is distributed to the neighboring LSRs. We had already discussed that we consider a node to be a downstream node with respect to another node if the packet flow is going to be in the opposite directions. Okay. So, essentially if there are two nodes in the networks, and if the packet flow is going to be from one node to another node, in one direction, and if the label allocation proceeds in the opposite direction, then we call it to be a downstream based label allocations. Now, we are saying that downstream based label allocations could be unsolicited or it could be on demand basis. Now, unsolicited label allocation, the trigger for the unsolicited label allocations normally will be the new routing updates or any topological changes or routing informations. On the other hand, on demand based label allocations can proceed when a node requests the allocation of a label. So, as we have discussed here, the downstream unsolicited label allocation, the trigger is the new routing information, and for the downstream on demand, it is the upstream label switch router which specifically requests a label assignment, and then the corresponding downstream routers will assign a label. Now, as we had discussed that label distributions can be done either by piggybacking the label bindings onto the existing control protocols like OSPF or Rsvp or some other routing protocols. An alternate approach of course would be to come up with a separate new protocol which is called as label distribution protocol, which has been standardized in the Mpls. Now, in the label distribution protocol, first there is an LSR discovery mechanisms. That means the protocol, the LDP protocol, actually first discovers the neighboring label switch routers, okay, through an LSR discovery mechanisms. 4 classes of messages have been defined in the label distribution protocol for label allocations, requesting a label, mapping a label. Okay. And the label distribution protocol essentially runs over TCP to provide a reliable delivery of messages. Of course, now this is an issue that you can build an inbuilt reliable mechanism onto a label distribution protocol, or you can make use of the existing transport protocol for the reliable delivery. Now, there are pros and cons against here. Now, note that the TCP has its own congestion control and flow control mechanisms built into it, which may not be required for the distribution of the labels in the label switched routers. Okay. So, that also the TCP requires a 3-way handshake mechanisms which introduces a further latency into the networks. However, it was decided in the MPLS standards body that LTP will run over a TCP as a TCP application and make use of the TCP's capabilities for providing the reliable delivery of informations, even though we may not need other features of TCP like congestion control or flow control mechanisms. The LDP is easily extensible using the messages which are specified as collections of type, length and value, as the TLV encoding is done for these messages in the label distribution protocol. Now, we come to So as we were saying that what are the advantages of MPLS? There are two major advantages of two major driving factors for the MPLS. One was the performance bottleneck in the IP routers due to the longest prefix match, which no longer currently a driving factor for the MPLS. But the other important driving factor for the MPLS was that it can address the challenges of traffic engineering in the IP networks. Okay. So, that is one of the major driving factor today for the deployment of the MPLS networks. Another important thing, as we will see subsequently, is that MPLS traffic engineering mechanisms also enables it to be as a control plane protocol for the DWDM based optical networks also. So, for an intelligent optical networks, the MPLS can serve as a unifying control plane mechanism. So, we will just see how MPLS is used for the traffic engineering purposes. Now, in MPLS in traffic engineering, the routes are established which are optimal with respect to a certain scalar matrix and which is subject to constraints on the available bandwidth on the individual links. So, what does it do is that it makes use of that constraint based routing algorithms. Okay. These constraint based routing algorithms essentially are similar to quality of service based routing algorithms. Now, there is a slight difference between the QoS based routing and the traffic engineering algorithms. In QoS based routing also, you will choose a path which will be optimal with respect to a certain metric and which will be subject to availability of bandwidth on the link. So, that is also done in the QoS based routing. But the difference between the QoS based routing and the traffic engineering algorithm is that the QoS based routings are typically greedy. Okay. So, once they choose a path, okay, which satisfies the certain constraints, and if another request comes and if that request can be accommodated by readjusting the load, that will typically be not done in a QoS based routing algorithms. However, a traffic engineering algorithms may try to readjust the loads in such a manner that the new request can be accommodated. So, that is really the difference between the quality of service based routing and the traffic engineering or a constraint based routing algorithms which are used in the traffic engineering. So, the MPLS will make use of the capabilities of these constraint based routing algorithms to determine paths which are optimal with respect to a certain scalar matrix and which can choose a path subject to availability of bandwidths on a particular link or so. Now, the traffic trunks are actually the collection of individual microflows. The MPLS actually defines a concept of a traffic trunk which can be a collection of individual microflows. That means several microflows are aggregated into traffic trunk, and then these traffic trunks are routed in the MPLS domain in the form of label switch paths, and these label switch paths are mapped onto the routes which satisfy certain constraints on of available bandwidth or delays etc. on the individual links, and these links are actually chosen by some form of constraint based routing algorithms. So, here is an example of this, that these are all label switch routers. So, for example, there may be some traffic which may be going from this node to this node. So, in a constraint based routing algorithms, you may select some traffic to go on this link, okay, and that may be an optimal path for this, but some traffic may get diverted onto this link. So, as a result, the constraint based routing algorithm may try to optimize the link capacity utilizations of this link and this link. So, the three links link capacity utilizations, the constraint based routing algorithms may try to optimize, and then what can be done is that a label switch path can be set up on this red line. The label switch path can be set up a priori here, and all the microflows can be aggregated into this traffic trunk, and this traffic trunk has been mapped onto this LSP, and it can be routed onto this label switched path. Of course, to establish these label switch path, you require the signaling protocols for the traffic engineering, and there are two approaches which were proposed. One is what is called as extension of the existing label distribution protocol to support the constraint based routing, and that approach was called CRLDP, or constraint based routing label distribution protocol. And another approach was the extensions of Rsvp TE, okay, that is extensions of resource reservation signaling protocols for the traffic engineering purposes. There were, of course, a lot of debate whether CRLDP is better or Rsvp TE is better. Some people argued that Rsvp TE has a scalability problem. Note that Rsvp was a signaling protocol which was proposed in the context of integrated services internet model of QoS, and from that the people had this argument that Rsvp TE has a scalability problem, but actually speaking, the scalability problem was more in the INTSER model rather than in the signaling protocols. Okay, so it was then favored by many people that Rsvp TE could be a better signaling protocol for traffic engineering purposes in the MPLS networks. Moreover, Rsvp extensions of Rsvp have also been proposed for setting up a guaranteed bandwidth label switch paths also. Okay, so even if you do not want to do the traffic engineering, but if you want to provide the quality of service guarantees in the MPLS based networks, then extensions of Rsvp also have been proposed to enable that. So because of these two things, the Rsvp TE as a signaling protocol was favored for the traffic engineering purposes. Okay, and that is and traffic engineering for the IP networks is, as we have argued, is the major driving factor for the MPLS networks, and therefore Rsvp TE is going to be one of the dominant signaling protocol whenever the MPLS networks will be deployed in the networks. Okay. Now we will look into how the model of QoS, the quality of service, the quality of the IP, how MPLS actually extends the QoS model of the IP networks. In fact, it was long believed that actually MPLS provides quality of service guarantees. However, actually that is not true. MPLS, really speaking, extends the IP QoS model. So therefore, if in an MPLS based networks, if you really want the quality of service guarantees, then actually you have to enable the IP QoS model only. Okay, so let us look at the MPLS and the quality of service. So MPLS actually supports, rather than it extends the IP QoS model. Okay, and the MPLS, however, does not run in the hosts. Okay, typically, the MPLS will be present in a label edge router. However, as you know that QoS is an end-to-end paradigm. Okay. So what is really meant is that MPLS can be used to provide the quality of service guarantees to the traffic trunks, or creating the label switched path which have guaranteed bandwidth or low delay qualities. But really speaking, the MPLS cannot enable an end-to-end quality of service guarantees, essentially because the MPLS starts, you start seeing MPLS only from the label edge router kind of thing. The MPLS may actually help service providers to offer the IP QoS services more efficiently. So even though MPLS inherently does not have any inbuilt QoS mechanisms, it actually relies on the IP QoS model only. It extends actually the IP QoS model. We will just see that how it can help the service provider to offer the IP based quality of service services in a more efficient manner. So as we had seen that the IP QoS model is of two types. We have had extensive discussions on this, that there are two major models. One is the integrated services, okay, and another one is the differentiated services. The integrated services model also is of two types. One is that provides the guaranteed service, one is provide the guaranteed service, and another one is the controlled load service. Now, as you know that in the guaranteed service, the individual flows are given hard guarantees in terms of absolute quality of service attributes, which is like bandwidth or end-to-end delay and so on. Okay. So, now what is done in the integrated services model is that individual packets are actually classified into several flows. Okay. And then and the classification is done based on these application flows. So, there may be as many virtual queues in the system as there are flows, and then the scheduler will schedule these flows in such a manner that we can provide absolute quality of service guarantees or hard guarantees, okay, in terms of either the delay bounds or the minimum rate or the bandwidth. Obviously, this model suffers from scalability problems, okay, in the sense that the scalability problems are that you have to classify the packets into individual flows, and therefore, the states corresponding to these individual flows will have to be maintained by the routers. Okay. So, to address these problems of integrated services, okay, a rather coarse grained QoS approach was proposed in the IP world, and that was called as the differentiated services. Now, in differentiated services, instead of classifying the packets into individual flows, you classify the packets into a fewer number of classes only. So, basically you aggregate these flows into classes and then classify the packets into these 3 or 4 classes only. At max, there may be it is widely believed that in the internet, if we already have a best effort networks class, if we have a better than best effort service model or a premium service model, that will be more than sufficient for most service providers, from the quality of service perspective. So, therefore, a rather coarse grain approach, that is the differentiated services approach, was proposed, which tried to alleviate some of the scalability problems that were existent in the integrated services approach. And the differentiated services based QoS model is likely to be more popular in the IP world. It is more scalable, it has less signaling overheads, and it has less overheads in terms of state maintenance. So, therefore, it is scalable QoS model and likely to be more popular. So, integrated services has a mechanism in terms of admission control. It has a classification engine. It classifies the packets into individual application flows. The admission control decides how many number of such flows can be admitted, so that when you apply the queuing and scheduling mechanisms, you can provide the assured quality of service guarantees. Once the flows are admitted, then the flows are also policed to see that the corresponding flow is conforming to its advertised traffic descriptors or not. And if it does not conform to the advertised traffic descriptor, then the router may either drop the packets or it may mark the packets, because it may affect the quality of service guarantees given to the other flows. The signaling protocol which is used in the integrated services is one of the most popular signaling protocol, which is resource reservation based protocol, or what is called as Rsvp. So, this is the signaling protocol which is used to convey the information about the traffic descriptor that a source is going to have, and the quality of service attributes which the source desires to have from the network. Now, Mpls actually extends the Rsvp protocol for signaling of the QoS. Now, what we have to do really is that if you have to extend the IP QoS model, then apart from conveying the quality of service attributes and the traffic descriptors, now the signaling protocol also has to convey the label bindings, okay, between this QoS state and the corresponding label switch path or the traffic trunk. So, what is done is that the creation of now the label binding is driven by the Rsvp, and for that purposes a new Rsvp object is defined, okay, which is called as a label object, which is carried in the reservation messages. Now, what is done here is that typically Rsvp sends a path message from the sender to the receiver. So, it will send a path message which will contain a traffic descriptor and a request for traffic descriptor, and essentially it will go from the sender to the destination. Now, the destination will initiate the reservation request giving the quality of service attributes, and along with that it will also initiate a label request message. So, a label object will also be carried in the reservation messages. You can see that only the first router in the LSP needs to be concerned with which packets belong to the reserved flows, unlike in the IP networks, because it is the first router which will do the packet classification of these IP packets into the corresponding FECs, which is associated with a certain QoS states. And later on, once the label switch path is set up, really speaking, the individual routers do not have to do the packet classification and associate them with the QoS state which has been signaled by the Rsvp, okay, which is normally done if the router was an int-serv router. So, this posed a as we had discussed, a scalability problem in the int-serv router. So, that problem is addressed in the Mpls networks automatically. So, typically in Mpls, if you want to provide the quality of service guarantees, you will be actually setting up a guaranteed bandwidth pipe or a guaranteed bandwidth label switch path for a large aggregate of traffic. So, that can be set up to provide quality of service guarantees. In Mpls, typically you will not be setting up a label switch path for individual application flows and associate them with a QoS state, because that, as we have seen, imposes a lot of scalability problem. Now, as we have seen, actually the Rsvp is a soft reservation protocol in the sense that the QoS state maintained by the Rsvp are typically soft, okay, in the sense that they require periodic refresh mechanisms. Okay. Unlike in the ATM world, where the QoS signaling state could be a hard signaling state, in Rsvp the signaling state is typically soft, and what is done is that it requires a periodic refresh mechanism. These QoS states need to be periodically refreshed. Okay. Now, if you do this in the Mpls, then the volume which will be generated by the refresh traffic, which would be very large, for the large reservations. Okay. So, it would be prohibitively very large. Okay. And moreover, the Rsvp does not operate it on the reliable delivery mechanisms. So therefore, Mpls has added in the Rsvp a reliable delivery mechanisms, in which the signaling message will contain a message ID, and that message ID will be periodically act. And so, as a result, what you can do is that you can increase the refresh timer interval. You do not have to send now the refresh states periodically for a shorter refresh interval. Now, the refresh interval can be made a little larger, and as a result we can reduce the traffic that is there due to the refresh packets. Now, we see how the differentiated services paradigm can be integrated with the Mpls. As we have already brought out, that differentiated services is more a coarse grain approach for providing quality of service guarantees. In this approach, what is really done is that the packets at the ingress of the differentiated services domain are classified into few classes, and once they are classified into few classes, this class is carried in the packet itself, which is called as differentiated services code point or DSCP. Okay. This DSCP bit actually was previously the IP TOS field, IP type of service field, and that IP type of service field has been redefined in the differentiated services to be a DSCP code point, differentiated services code point. So, as a result, what happens, just like in the MPLS, so the paradigms are quite similar. Just like in the MPLS, where the packet classification is done at the edge of the network, packets are classified into forwarding equivalence class, and FEC is bound to a label, and then packet is attached with a label, and then in the core of the networks, it is the label which is used to forward the packet to determine the next hop or the next label. Similarly, in the IP differentiated services model also, packets are classified at the edge of the differentiated services domain into few classes. Okay. Now, corresponding to each class, we have a differentiated services code point. So, that code point is then encoded into the packet and the packet is sent. Now, in the core of the differentiated services domain, no more packet classification is done on the IP header or on the TCP header, etc. That has been already done at the ingress of the networks. However, the core of the networks now will look only at the differentiated services code point, only they will look at the DSCP point, and this DSCP point will determine what treatment, what forwarding treatment the packet should get. So, this is the principle of the differentiated services. Now, as you can see, the paradigms of the forwarding are very similar in the MPLS in the differentiated services. It would have been very good, if there have been an alignment of the DSCP or a differentiated services field along with the MPLS label field. But since the two were defined separately, as a matter of fact, the differentiated services was defined much earlier to the definition of the MPLS label. So, when we need to extend the differentiated services paradigm to the MPLS world, the problem was how do we map these differentiated services classes to in the MPLS. Now, one way could have been that in the MPLS, as we had seen that in the label there is a 3-bit EXP field, experimental field, which was put. Now, we can map therefore the differentiated services classes by using this 3-bit of the EXP field. Okay, we can use that. Unfortunately, however, that in the differentiated services model, there are 6 bits, which have been used to define the differentiated services classes. So, therefore, theoretically, there are 2 raised to power 6 or 64 differentiated services classes are possible. Now, in the MPLS, we only have 3-bit. So, therefore, only 8 bits are possible. So, now the question is, how do we map these 64 classes into these 8 classes which are possible with the MPLS network? It was argued that in many cases, actually in most IP QoS network, 64 classes are not going to be implemented mostly. Mostly in the differentiated, when the differentiated services is deployed in the IP world, more than 8 classes are unlikely to be there. Now, this solves the problem to a large extent. If in a particular network, if not more than 8 differentiated services classes are to be deployed, then the EXP bit, the 3-bit EXP bit can be used to determine the differentiated services class in the MPLS network, and that in turn can determine the forwarding treatment which corresponding labeled packets will get in the network. Now, when we set up LSPs in this manner, then they are called eLSP. eLSP, E stands for that we are using essentially the EXP bit, okay, the 3-bit EXP bit to denote the corresponding differentiated services class. Okay. However, in cases where more than 8 classes are to be deployed, then obviously some portions of the label must be used. Okay. So, some part of the 20-bit label that needs to be used, and that is what is called as llsp. Okay. Now, let us see how that is done in the MPLS. As we have already seen that in the differentiated services, we do not require a per flow state information. Edge router will classify the packets into Diffserv, and classes are encoded in the differentiated services code point, and the differentiated services code point essentially identifies a per hop behavior. Now, one more thing which I would like to point out here is that in the integrated services model, the paradigm was more an end-to-end QoS model. In the differentiated services model, it does not define actually the services, but it actually defines the forwarding treatment. Now, the value of the class which is carried in each packet through the form of differentiated services code point will determine, okay, what is the forwarding treatment that a packet will get, and it will not determine what is the service that the packet is getting. The services, end-to-end services, needs to be created by a combination of the forwarding treatment which each router has to give in conjunction with some other mechanisms like admission control or policing at the edge of the router. So, services by the service provider needs to be created out of these Legos or out of these components of the differentiated services. So, as we were discussing, that we need to then map the DSCP field to the label. So, since the DSCP has 6 bits supporting possible 64 classes, we can use the EXP field of the shim header, but since EXP field is just 3 bit, so what is the solution? Now, one observation, as we have seen, that if the network supports fewer than 8 PHPs, then we can use the EXP bits, and LSP setup under these conditions is called eLSP. Okay. But what if we need more than 8 PHPs, then obviously, as we were just discussing, we need to provide information inside the labels. Okay, we need to provide information inside the labels, and this requires now enhancing the label distribution protocol also, because labels are now need to be bound to both FEC and the per hop behaviors. Okay, so this binding needs to be done, and therefore that requires an extension of the label distribution protocol, and actually such LSPs are called llsp as opposed to the eLSP, where we are using that 3-bit of the experimental field of the MPLS. Now, in llsp actually the packets which belongs to the different PHBs. Now, it may so happen actually that packets may belong to the different per hop forwarding behavior, but you want that these packets should not be reordered. So, therefore, all those packets which belong to the different PHBs, but these packets should not be reordered, they form one PHB scheduling class. Okay. And it is therefore mandatory that packets belonging to the same PHB scheduling class must travel on the same LSP. So, this point needs to be taken into account while setting up an llsp in the MPLS network. Now, obviously, the question then arises is that if we have bound a PHB scheduling class to a label, because what we are now saying is that packets which belong to the same scheduling class, they are bound to now an LSP, and therefore the label now identifies the PHB scheduling class. But now, how to determine the different PHBs of a PHB scheduling class? Then in that case, we can take the help of the 3 bits of the experimental EXP bits. We can take the help of EXP bits to determine that from this PHB scheduling class, how the different PHBs, what are the different PHBs which are present. Okay. So this way, one can determine the different PHBs of a PHB scheduling class also. So what we have seen is that, so in conclusions, what we have really seen is that the Mpls extends the QoS model of the IP networks, so first of all, it needs to extend the signaling protocol of the QoS model like Rsvp, because now you have to not only bind the labels to FEC, but you have to also bind the label to the corresponding QoS states. So when we want to bind the LSP to the corresponding QoS states, like in the differentiated services, obviously the question then is that how do we identify the different QoS states? So we can identify the different QoS states by using those 3 bits which are present in the label in the form of EXP. But then the problem is that there are only 3 bits, so therefore only 8 possible QoS states will be available. Now if you want more than 8 possible QoS states, then we can use the label, the part of the label themselves to identify the corresponding QoS states. Okay. So this way we can extend the IP QoS model to the Mpls network. Now this essentially completes our discussion of how Mpls can be used to alleviate the problem of longest prefix match in the IP networks, which is very simple, because instead of using forwarding based on IP addresses, we are using based on labels, which can be and the label lookup can be simply done in the form of an index lookup. The second problem is that the Mpls enables the traffic engineering in the IP networks, and that is done essentially by using the capabilities of constraint based routing algorithms and extending the Mpls signaling protocol to establish routes which are optimal with respect to load balancing in the IP world. And the third thing is that Mpls extends the IP QoS model, either the integrated services or the differentiated services model. So these are the 3 features or enabling applications of Mpls that we just discussed as a part of this lecture. Now what we will discuss further in this lecture is that the Mpls can also has a novel application, and that is that Mpls can also be used as a control plane for the next generation intelligent IP networks, IP optical networks. Okay. So in the next few minutes we will see that how Mpls can be used as a novel signaling or a control plane protocol for the intelligent optical networks. So let us see how Mpls as a control plane it can be used for intelligent optical networks. Now before really we go into this, let us see how the today's optical networks are built. So here is a slide which shows how a multi-layer optical networks is built. Now you can see the physical layer could be based on a optical DWDM networks, dense wavelength diffusion multiplex network, and which can be used essentially to increase the capacity of a optical networks. Today we can build a DWDM based networks for 40 gigabit per second kind of capability. Then we have this Sonnet SDH kind of networks. Essentially we can have a DWDM ring, then we can have a ring of SDH, and SDH basically provides both the multiplexing as well as protection and restorations capabilities. The protection and restorations capabilities are inherent in an SDH based networks, and then we have the ATM which runs over the SDH. And ATM is the primary transport protocol which is used for the various services integration and provides an information transport mechanism over the fiber based SDH or the DWDM networks. And then we get those IP or internet services by running IP over all these protocols. So as we had seen here in our previous discussions also, that at the physical layer you can have this SONET SDH ring or DWDM ring as the physical layer, and ATM is actually used as a transport mechanisms which provides the traffic engineering capabilities, and which provides a multi-services integration, which provides basically an information transport protocol, and over which the IP network is run. And this is what we had discussed earlier, is like an overlay model where IP is being run over an ATM. Now we see how the next generation network is evolving, and as you can see here that a next generation network is rapidly evolving from IP ATM SONET DWDM networks to IP MPLS over SONET DWDM. So you can, as you can see here, that this ATM layer has been completely removed. ATM layer was basically used for providing traffic engineering capabilities, for providing QoS capabilities, for providing transport capabilities. All that job is now done by the MPLS networks. The SONET or SDH is still present for providing the multiplexing or protection capabilities. And as we are gradually moving to the next generation networks, as you can see that some networks are now being built where we no longer have a SONET or SDH ring, but we have a pure fiber ring as well, where the IP MPLS protocol is run in a native mode over this fiber ring. In fact, as we will see that in the next generation optical networks, we are going to have a fiber based Ethernet rings also, where the Metro Ethernet based services are going to be provided, and MPLS actually provides a mechanism by running MPLS over Ethernet. It provides a mechanism for multi-services integration and for providing traffic engineering capabilities. Alternately, if you are not using the 1 gig or 10 gig Ethernet ring, we can use a DWDM based ring also to provide more capacity like 40 Gbps and so on, and then MPLS can be run over that networks for multi-services integration. So this is now going to be an evolution to a next generation optical networks, where SONET and SDH may be replaced by MPLS DWDM or MPLS 10 gig Ethernet combinations. So this is an evolution to basically a next generation network, and we will see here what is the role really of an MPLS networks here. Now, as we can see here that SONET SDH basically provides an important protection and restoration capabilities, what is called as 50 millisecond restoration times, and this is historically this was historically very important for providing certain time critical services like voice, the public switch telephone network quality voice, the PSTN or the TDM quality voice. The SONET SDH was providing an important function of having a sub 50 millisecond protection and the restoration capabilities. And when we chop off the SONET SDH ring and come up with the MPLS Ethernet or the MPLS DWDM ring, then we need to see that those kinds of protection and restorations capabilities are being enabled by these networks. Okay, so that is how we will see whether it is possible to enable that in the IP MPLS based networks, how that gets enabled, and how actually we will evolve to a next generation optical networks. And the key there is that since MPLS has this traffic engineering capabilities, that can be used as the cornerstone or the starting point to enable an MPLS as a control plane protocol for configuring these next generation DWDM based optical networks. So what we are now saying therefore is that how IP directly can be run over optical networks. So first let us see that we are having directly IP over DWDM, and what are the challenges there and how MPLS actually will be used to address those challenges. So there are two models quite similar to when we were discussing IP over ATM networks. So one is the overlay model, and another one is the peer model. Now, in the overlay model, the OTN, that is optical transport network, and which could be based on DWDM, is completely opaque to the IP networks. Okay. So, therefore, we have two separate control planes, very similar to the discussions that we had for IP over ATM. So, one control plane will operate within the optical networks, and other control plane will operate between the core optical networks and the edge router. So, there are two separate control planes. IP routing is separate, the wavelength routing or optical routing is separate. So, this is very similar to the IP ATM overlay model. But then we have a peer model where there is a single control plane for optical and IP networks, and optical routes, or what are called as light paths, they are derived from the IP routing knowledge. Okay. So, they are actually derived from the IP routing knowledge. There are no two separate control planes. Now, here there is an important point to make. Now, as we have seen, when we discussed this overlay model in the context of IP over ATM, to address the problems of the IP over ATM, we said that in a peer kind of a model, an MPLS based networks actually provides a peer model. Now, in this context, we will see that an MPLS can also be used as a single control plane protocol even for the integration of optical and IP networks. So, that is really an advantage of that. So, this is how an overlay and peer model will look like. This is an underlying optical network which is there in the core of the network, which is essentially a wavelength routed network, and these are IP routers at the edges of the networks, and the entire network has been overlaid over a wavelength routed based networks. Now, these optical routes are derived by using a separate wavelength based routing, and the IP routes are derived using the IP routing protocol. But this is here a peer model where the optical routes or the light paths, they themselves have been derived from the knowledge of the IP routing. So, essentially this wavelength routing protocol is also participating in some form of IP routing. Now, let us look at the overlay model. There are two possibilities in the overlay model. Either you can have a static overlay model, or you can have a dynamic overlay model. Now, in essentially what happens is that in the static overlay model, the light paths have been statically provisioned. Okay. So, the light paths are essentially basically statically provisioned, and in the dynamic overlay model the wavelength provisioning using wavelength routers is used, and wavelength based routers are essentially nothing but optical cross connects, and they may have a IP routing intelligence. Okay. So, the two separate distinctions are there. One is the static overlay model, another one is the dynamic overlay model. Both are overlay model. They are not peer to peer model in the sense that light paths are not derived from the knowledge of the IP routing, but in the static overlay model the light paths are statically provisioned, and in dynamic overlay model the light paths are provisioned using wavelength based routing. Okay. Using wavelength based routing protocols the light paths are provisioned in the dynamic overlay model. And basically what we are saying is that these are optical cross connects with some intelligent routing. Now, if you consider the protection and the restorations which is available in the static overlay model, then the protection mechanism is basically limited at the optical transport layer only, if you see the static overlay model, and there may be some restorations capabilities which may be available at the service layer. For example, if we are using an SDH networks, then you may exploit the automatic protection switching capabilities which are there in the SONET, including the intelligent protection switching, or we may exploit the restoration at the IP layer. But as you will see subsequently, that the restoration at the IP layer is extremely slow, and it does not conform to the sub 50 millisecond restorations capabilities which are typically required at by the optical networks. If you see restoration at the IP layer, then we have really a large restoration times. So, by the time the IP routing protocol discovers that some node or link has failed, and then try to recover from this and try to establish or restore a new path, you may take several seconds. Of course, you can alleviate this problem by decreasing the timer values in which you have to send the routing updates, because typically you will send the routing updates only after the expiry of the timer, and you can decrease this timer value. However, the disadvantage is that it leads to excessive amount of traffic, and we can use a combination of layer 1 and 2 mechanism to detect the link failures and report it to the routing engine, and this can be used by the IP routing protocols. Now, the thing is that if you are just using the IP routing, then we have the same problem, that protection and restorations really is very difficult by just using the IP layer. Now, what therefore one can use is that we can, instead of IP routing, we can use MPLS based restoration mechanisms that may be little faster than simple IP routing. Now, how does this MPLS based protection and the restorations will work? So, we are still talking in the context of overlay model only. So, we have the at the edges those IP routers which are overlaid over this optical cross connect or wavelength based routers, but now we are actually talking of restoration which will be available at the IP layer. So, maybe these IP routers now maybe are the MPLS routers. Okay. So, they are not so what we are saying now is this MPLS network is overlaid over the optical networks, and try to use the MPLS based protection and restorations capabilities. So, in MPLS, you can do a pre-negotiated protection, that is in the sense that backup path can be configured statically. So, there is a primary labels, what is called as primary label switch path, okay, where you will be sending your data in the normal course, but whenever that primary label switch path breaks down, then you will start forwarding the data on the alternate paths. So, and you can determine the bandwidth of the backup path either in advance, or you can dynamically allocate it. So, this is like a pre-negotiated protection. You have already set up a backup path. A dynamic protection would mean that a backup path can be created on demand. So, obviously, this will have some setup time. Mostly in the MPLS we can use 1:1 protection mechanism in the MPLS, in the sense that for every primary LSP you can have a secondary LSP as the backup path. So, this is how MPLS based protection will operate. So, these are all so this is, here is a primary LSP from A to B, which is shown in the red color here, and here is a backup LSP which is shown from here. Now, in the normal course the packets will be forwarded on this primary LSP, that is this red line, but let us say any of these links breaks down, then and when this is discovered by this label edge router, then the packets will actually start forwarding on the backup LSP. So, this way we can provide a protection mechanism in the overlay model itself. Now, the next step of course would be to see how the MPLS with its traffic engineering capabilities can be used as an integrated control plane for a peer-to-peer model as well, and that is like an extension of MPLS to optical networks, which is what is called as GMPLS, or generalized multi-protocol label switching protocol, generalized multi-protocol label switching. So, we will discuss this in the subsequent lectures, that how MPLS with its traffic engineering capabilities and protection and restorations capabilities can be used to provide an intelligent peer-to-peer optical network.